Every single day, over 28,000 freight trains crisscross America, hauling 1.6 billion tons of cargo worth over $700 billion annually. But what you don't know about these mechanical titans could blow your mind. A retired locomotive engineer from BNSF Railway's maintenance facility in Havre, Montana, recently revealed to me the jaw-dropping truth. These machines aren't just trains. They're rolling laboratories of engineering genius that most people will never see or understand. Today, I'm revealing 14 mind-bending innovations hidden inside every locomotive that will change how you see trains forever. And when you see number 4, you'll discover a mechanical marvel that operates using nothing but engine vibration, saving railroads millions of dollars for decades. Before we dive in, hit that like and subscribe button, because what you're about to learn could make you the most knowledgeable person at your next dinner party. Let's start with the most amazing one. Number 1, the self-rotating piston phenomenon. Inside a massive locomotive engine are the pistons, chunks of metal the size of dinner plates, are literally spinning inside their cylinders like they're dancing to music only they can hear. This isn't science fiction. This is EMD engineering at its finest. These pistons rotate a full 360 degrees using absolutely zero external power. No motors, no gears, no computer control. Just pure mechanical genius harnessing the chaotic vibrations of a 4,000 horsepower diesel engine. This innovation emerged in the 1960s when EMD engineers were struggling with uneven cylinder wear patterns that were shortening engine life. Traditional automotive pistons wore unevenly, creating hot spots and premature failure. EMD's solution was born from studying how vibration affects metal components over time. The engineering is elegantly simple. The pistons sit on a carrier with a groove cut into the piston itself, held by a massive snap ring. As the engine runs, the natural vibrations cause the piston to slowly rotate. It's like the engine is unconsciously giving itself a massage to stay healthy longer. Just like wearing the same pair of shoes every single day for 20 years, but somehow they wore evenly on all surfaces instead of just the heel and toe. That's exactly what these rotating pistons do for the engine. They ensure perfect wear patterns on all sliding surfaces, maintaining the crucial cross-hatching on cylinder walls that keeps oil flowing properly. One locomotive mechanic told me he's seen engines with over 2 million miles, where the pistons still look nearly new because of this rotation. In car terms, that's like driving to the moon and back 4 times with barely any engine wear. This rotating piston concept has influenced marine diesel engines and large stationary power generation equipment, where similar wear patterns needed to be addressed. Number 2, the guru valve. This little mechanical marvel might be the most underappreciated piece of engineering on the entire locomotive, and it operates on principles so simple they're brilliant. Unlike your car, locomotives don't use antifreeze. They use a water borate solution that will absolutely freeze solid if temperatures drop too low, and when water freezes, it expands with the force of a bomb. The guru valve was developed in the 1950s when railroads were losing hundreds of thousands of dollars annually to freeze damage. Before this innovation, locomotive crews had to manually drain cooling systems during winter shutdowns, a process that was often forgotten or done incorrectly. The guru valve was a mechanical thermometer, an automatic valve rolled into one device. When temperatures hit 35 to 40 degrees Fahrenheit, this device automatically opens and dumps every drop of coolant from the engine, preventing a catastrophic freeze-up that could cost hundreds of thousands of dollars. The most amazing part? It needs zero electricity, no computer control, no human intervention. It's pure mechanical intelligence. A spring-loaded valve that responds to temperature changes with the precision of a Swiss watch. One railroad maintenance supervisor told me that guru valves have saved his company over $3 million in engine replacements during just one particularly brutal Montana winter. 3. Dynamic weight management. Modern locomotives can literally change their weight distribution while rolling down the track at 70 miles per hour. BNSF's GE locomotives equipped with dynamic weight management systems do exactly that. This system was developed in the 1990s when railroad companies were pushing for heavier trains and steeper grades. Traditional locomotives would lose traction on inclines, requiring additional power units or speed reductions that hurt efficiency. If a 15,000-ton freight train was pushing up a steep grade and your locomotive wheels start slipping on the rails, in the old days, you'd have to slow down, maybe even stop and radio for help. But with DWM, the locomotive literally lifts its middle wheels slightly, putting more weight on the outer wheels where the traction is needed most. The system uses pneumatic cylinders, basically giant air-powered pistons, to push on a bar connected to a cam lock rod. When that rod rotates, it raises a massive but short chain connected to the idler wheel carrier. It's like the locomotive is doing a subtle weight shift, like a gymnast adjusting their balance mid-routine. One engineer described it to me as teaching a 200-ton machine to dance. The locomotive can increase its tractive effort on command, turning potential wheel slip into maximum pulling power. It's the difference between a train that gets stuck and one that conquers any grade you throw at it. This all happens automatically, with computers monitoring wheel slip and adjusting weight distribution faster than any human could react. It's like having a mechanical nervous system that never gets tired. 4. The 3-in-1 alternator. Most people think of locomotives as simple machines, but the electrical system alone would make a Tesla engineer weep with admiration. At the heart of this electrical marvel is the 3-in-1 alternator generator, a single unit that serves 3 completely different purposes. This came about in the 1960s when locomotive manufacturers realized they were installing separate generators, alternators, and starter motors, creating weight, complexity, and maintenance issues. The solution was to combine all 3 functions into one unit. One set of windings generates electricity solely for the traction motors, which are the massive electric motors that actually turn the wheels. These motors are electrical gluttons, consuming most of the locomotive's power output. The second set of windings powers everything else: lights, computers, air conditioning, the coffee maker in the cab. When the engine needs to start, this same alternator becomes a motor. Apply electricity to it, and it spins the massive diesel engine to life. It's like having a device that's simultaneously a generator, a power distribution center, and a starter motor all in one compact package. The efficiency is staggering. Instead of having 3 separate systems taking up space and adding complexity, locomotive engineers created one elegant solution. One maintenance chief told me that this design alone saves roughly 2,000 pounds of weight and countless hours of maintenance time compared to separate systems. 5. The summer-winter door. You know how your body shivers to generate heat when it's cold? Locomotives have their own version of this survival mechanism, and it's called the summer-winter door system. This seemingly simple feature represents decades of engineering refinement to help massive diesel engines run efficiently in everything from Arizona desert heat to North Dakota winter conditions. This system was developed in the 1970s after railroads experienced significant power losses and engine failures during extreme weather conditions. Engineers needed a solution that would work automatically without crew intervention. Located on the engineer's side of GE locomotives, this door looks unassuming, just another panel in the sea of locomotive bodywork. But its function is pure genius. During warm months, the door stays closed, and the prime mover draws all its combustion air from outside. Simple enough. But when winter arrives, that door opens, and the engine starts breathing differently. Now it's pulling warm air from the engine compartment and mixing it with cold outside air. The result? The engine gets pre-warmed air, which burns more efficiently and keeps the massive diesel running smoothly even when the outside temperature could freeze your coffee in minutes. It's the kind of simple, elegant solution that makes you wonder why every cold weather machine doesn't have something similar. The engineering principle is straightforward, but the real-world impact is huge. The difference between a locomotive that can work in any weather and one that becomes an expensive paperweight when the temperature drops. 6. The power assembly. EMD's power assembly system works like building blocks for locomotive engines, individual modules that can be swapped out without tearing apart the entire engine. This innovation revolutionized locomotive maintenance forever. This modular concept was developed in the 1980s when EMD recognized that traditional engine repair methods were too time-consuming and expensive. A single-cylinder failure could sideline a locomotive for weeks while the entire engine was rebuilt. Each power assembly is essentially a complete cylinder in a box. Piston, valves, coolant passages, gas pathways, injector mount, and valve cover all integrated into one replaceable unit. When something goes wrong in one cylinder, instead of tearing apart the entire engine block, mechanics can swap out just that one power assembly. The genius is in the disaster containment. When a locomotive engine has a catastrophic failure, maybe a valve drops, or there's a hot spot that damages the cylinder, the trauma is confined to that single power assembly. The main engine block, which would cost a fortune to replace or repair, stays intact. A maintenance supervisor in Kansas told me about a locomotive that threw a rod so violently it should have destroyed the entire engine. But because of the power assembly design, they replaced one unit and the locomotive was back in service within 48 hours instead of being scrapped. The economics are staggering. A complete engine replacement might cost $500,000 and take weeks. A power assembly replacement costs about $15,000 and can be done in a day. It's like the difference between replacing your entire car because the transmission failed versus just swapping out the transmission. This modular approach was so successful that it influenced engine design across multiple industries, from marine propulsion to power generation equipment. 7. Bulletproof windows. Most people worry about traffic when they're driving. Locomotive engineers worry about rocks, bullets, and debris flying at their windshield at 70 miles per hour. That's why locomotive windows aren't just glass, they're layered armor designed to stop small bullets and deflect projectiles that would shatter regular glass. This safety feature was developed in the 1980s after a series of incidents where engineers were injured or killed by projectiles striking locomotive windows. The railroad industry needed a solution that provided both protection and visibility. The front-facing windows are constructed with multiple layers of specialized glass held together with industrial-strength adhesives. It's similar to automotive safety glass, but engineered to withstand impacts that would make a car windshield look like tissue paper. We're talking about glass that can stop .22 caliber bullets and 9mm rounds. Why is this necessary? Railroad rights-of-way cross through every kind of neighborhood, from peaceful suburbs to areas where people, unfortunately, sometimes take target practice at passing trains. Engineers have reported everything from thrown rocks to actual gunfire, and these windows have saved countless lives. The engineering challenge was creating glass strong enough to stop bullets, but clear enough to provide good visibility in all weather conditions. The solution involves laminated layers with specific thickness ratios and adhesive properties that distribute impact forces across the entire window surface. This bulletproof glass technology has influenced armored vehicle design and has been adapted for use in buses operating in high-risk areas. 8. The aux cab. Behind every locomotive cab is a hidden room that most people never see and definitely shouldn't enter without proper training. It's called the aux cab, and it's essentially a chamber of electrical death that's been made safe through brilliant engineering. This automatic safety system was developed in the 1970s after several fatal electrocutions occurred when maintenance workers entered energized electrical compartments. The railroad industry needed a foolproof way to ensure worker safety. This cramped space houses the bus bars and electrical connections that distribute power throughout the locomotive. We're talking about enough electrical current to power a small city, running through exposed conductors that could kill you instantly if touched. It's like having a miniature electrical substation crammed into a space the size of a large closet. The genius is in the safety system. Every AW-cab has either an automatic sensor or a manual lever at the entrance. Step inside, and all auxiliary power shuts off automatically. It's like having a safety net that's always watching, ensuring that no one can accidentally electrocute themselves while working on the locomotive's electrical systems. The engineering challenge was creating a system that could instantly and safely shut down massive electrical loads without damaging sensitive electronic equipment. The solution involves sophisticated switching systems that can handle the electrical equivalent of turning off a lightning bolt without creating dangerous arcing or power surges. 9. Replaceable piston heads. General Electric took a different approach to the piston wear problem than EMD's rotating pistons, but their solution is equally brilliant. Instead of making the entire piston spin, they made the part that wears out most, the piston head, easily replaceable. This innovation came about in the 1990s when GE engineers realized that most piston failures occurred at the head, where combustion forces are concentrated. Rather than engineering a complex rotation system, they focused on making replacement simple and cost-effective. The piston head is where all the action happens. It's the surface that gets hammered by combustion forces, exposed to extreme temperatures, and subjected to the kind of abuse that would destroy normal materials in minutes. In traditional engines, when a piston head gets damaged, you replace the entire piston, an expensive and time-consuming process. GE's solution was elegantly simple: make just the head replaceable. When damage occurs, whether from a valve timing issue, a hot spot, or just normal wear, mechanics can swap out just the head, leaving the rest of the piston assembly intact. The time savings alone are revolutionary. Instead of a complete engine teardown that might take days, a piston head replacement can be done in hours. One maintenance chief told me that this design feature alone increased his shop's productivity by 30% during heavy maintenance periods. But the real genius is in the engineering of the connection between the head and the piston body. It has to be strong enough to withstand explosive forces, precise enough to maintain proper compression ratios, and simple enough that it can be serviced in the field. 10. The traction motor cooling system. Those distinctive protrusions on the sides of older EMD locomotives aren't just cosmetic. They're part of an ingenious cooling system that protects some of the most expensive components on the entire machine. Each traction motor costs about $20,000, and there are typically 6 of them per locomotive. That's $120,000 worth of motors that absolutely cannot be allowed to overheat. This cooling system was developed in the 1950s when locomotive manufacturers first began using electric traction motors. The challenge was cooling motors that generate tremendous heat while being constantly vibrated, bounced, and subjected to harsh conditions. The system works like a sophisticated air conditioning network for electric motors. Massive blowers at the back of the locomotive create airflow that's directed through those distinctive side protrusions, down under the walkway, and into a series of ducts that terminate at each traction motor. The engineering challenge was creating adequate cooling for motors that are generating tremendous heat, while being constantly vibrated, bounced, and subjected to the harsh environment under a locomotive. The solution involved aerodynamic ducting that maintains consistent airflow even when the locomotive is moving at speed and encountering crosswinds. 11. Positive train control. Modern locomotives are equipped with what amounts to a robotic co-pilot that never gets tired, never loses focus, and has perfect memory of every speed limit signal and track condition. It's called positive train control, and it represents the biggest safety revolution in railroad history. PTC was mandated by Congress in 2008 following several tragic accidents caused by human error. The system took over a decade to implement industry-wide, requiring unprecedented cooperation between railroads and technology companies. The system uses GPS positioning, onboard computers, and radio communication to continuously monitor the train's speed, location, and upcoming track conditions. If the computer calculates that the train won't be able to stop before a red signal or slow down for a speed restriction, it automatically applies the brakes, whether the engineer wants it to or not. The technology is remarkable in its complexity. The system knows the exact weight of the train, the grade of the track, the weather conditions, and the stopping distance required. It performs these calculations thousands of times per second, creating a constantly updated safety envelope around the train. One engineer described it as having a really smart backseat driver who's actually right all the time. The system prevents human error without interfering with normal operations. It's only when something goes wrong that PTC steps in and takes control. The implementation required upgrading tens of thousands of miles of track with radio equipment, installing onboard computers on every locomotive, and creating a communications network that rivals anything the military uses. The cost was in the billions, but the safety improvements have been dramatic. The impact: train accidents caused by human error have dropped by over 80% since PTC implementation began. This technology has influenced similar safety systems in aviation and maritime industries. 12. Distributed power. Distributed power systems allow engineers to control multiple locomotives scattered throughout a mile-long train from a single cab, like conducting an orchestra where the musicians are spread across several city blocks. This technology has revolutionized how heavy freight trains operate. This system was developed in the 1990s when railroad companies were running increasingly longer and heavier trains. Traditional configurations with all locomotives at the front were creating excessive stress on couplers and limiting train length. The system uses radio communications to control helper locomotives positioned mid-train or at the rear of long consists. The lead locomotive sends commands to the remote units, coordinating acceleration, braking, and power distribution across the entire train. It's like having multiple engines in a car, but each one is a quarter mile away from the others. The physics benefits are enormous. Instead of having all the pulling power concentrated at the front of the train, power is distributed along the entire length. This reduces the stress on couplers, decreases the likelihood of derailments, and allows trains to handle grades that would otherwise require multiple locomotives at the front. The radio communication system has to be incredibly reliable. If communication is lost, the remote locomotives automatically go into a safe mode, maintaining speed and braking capability while trying to re-establish contact. The fuel efficiency improvements are substantial. By optimizing power distribution and reducing train resistance, distributed power systems can improve fuel economy by 10 to 15% on long, heavy trains. For a railroad burning millions of gallons of fuel annually, that's a significant cost savings. 13. Regenerative dynamic braking. When a locomotive needs to slow down, it doesn't just use friction brakes like your car. It essentially turns the traction motors into generators, converting the train's kinetic energy back into electricity. It's like having a hybrid car system, but scaled up to handle trains weighing 15,000 tons. This technology evolved from traditional dynamic braking systems in the 2000s, when railroad companies wanted to capture the energy that was being wasted as heat. The concept was borrowed from electric vehicle technology but scaled up dramatically. The process is elegantly simple in concept, but incredibly complex in execution. The traction motors that normally propel the train are switched to generator mode, creating electrical resistance that slows the train while producing electricity. In traditional dynamic braking systems, this electricity is dissipated as heat through massive resistor grids, but regenerative systems feed the power back into the electrical grid. The energy recovery is substantial. A heavy freight train descending a mountain grade can generate enough electricity to power hundreds of homes. Instead of wasting this energy as heat, regenerative systems capture it and put it back to work. The environmental impact? By reducing brake wear and capturing energy that would otherwise be wasted, regenerative braking systems reduce both maintenance costs and environmental impact. This technology has influenced similar systems in electric buses and trucks. 14. Predictive maintenance. Modern locomotives are equipped with hundreds of sensors that monitor everything from engine temperature to wheel bearing vibration. This data is transmitted in real time to maintenance facilities where artificial intelligence systems analyze patterns and predict failures before they occur. This system developed in the 2010s as sensor technology became cheaper and data processing more powerful. Railroad companies realized they could prevent expensive failures by monitoring equipment health continuously. The monitoring systems are incredibly sophisticated. Sensors measure vibration patterns, temperature fluctuations, oil pressure variations, and electrical anomalies. The AI systems have been trained on decades of failure data, allowing them to recognize the subtle signs that indicate a component is beginning to fail. One maintenance supervisor told me about a locomotive that was flagged by the predictive system for a potential bearing failure. The locomotive was running normally, with no obvious symptoms, but the AI detected vibration patterns that indicated bearing wear. They brought the locomotive in for inspection and found the bearing was indeed failing. Without the early warning, the failure would have occurred on the road, potentially causing a derailment. The economic impact is enormous. A bearing replacement in the shop might cost $2,000 and take a few hours. The same repair done as an emergency road call could cost $20,000 and take days. The system is constantly learning and improving. Each failure that occurs provides more data for the AI to analyze, making future predictions more accurate. It's like having a maintenance expert who never forgets anything and gets smarter with every repair. This predictive maintenance technology has been adopted by airlines, shipping companies, and manufacturers, fundamentally changing how complex machinery is maintained across industries. The railroad industry continues to evolve, with new technologies being developed every year to make these amazing machines even more efficient, safer, and more environmentally friendly. The future of locomotive engineering is just as exciting as its past, and we'll be here to explore it all with you. If you enjoyed learning about these amazing engineering marvels, make sure to subscribe for more deep dives into the world of trains. Until next time, keep your eyes on the rails and your mind open to the amazing technology that surrounds us every day.